So in the last class, I told you that there is also relevance for the pressure term. Some of you asked why we did not consider the pressure term in the scale analysis, right? So when we looked at this inner coordinates or inner turbulent boundary layer, we did not consider the pressure term also in the outer layer. But I did mention that pressure will also become relevant. We discussed these three important sublayers within an inner layer. That is, we have this inertial sublayer here, where the turbulent terms are dominant, and we also saw that in the outer layer equation, the left hand side inertial term balances the turbulence term to first order, and in the buffer layer both the turbulence term and the viscous term balances to each other to first order. And then I said, when we go to this linear sublayer where only viscous effects are dominant, turbulence is negligible, then how can we leave this term by itself? Somebody must balance this, right? This is where, in the linear sublayer, this is where the pressure term is balancing the viscous term to first order. Let us say if you have a pressure driven channel flow, okay, so you are imposing a pressure gradient minus dp dx in your pipe flow or a channel flow, then this new du bar by dy is the friction that it is opposing and balancing the driving pressure gradient. They has to balance each other to first order. So the pressure gradient becomes dominant in the linear sublayer. Okay, this is clear? Okay. So now we go back to our turbulence modeling. So in the last class we looked at Boussinesq hypothesis, right? We started with what is called an eddy viscosity model. Eddy viscosity models under the framework of the Rans models. Okay, Rans model is little bit bigger, you can have many different class of models. So we started to look at eddy viscosity models. In that we learned what is a Boussinesq hypothesis. So we had 6 unknowns. So minus ui prime uj prime over bar. We had 6 unknowns, and this is of course the exact terms. This is now being modeled using Boussinesq hypothesis as 2 nu t Sij mean strain gradient minus 2/3 k delta ij. Okay. So here of course this is the modeled part. So 6 unknowns is now replaced with 2 unknowns, that is this and this. So 2 unknowns now, 2 unknowns nu t comma k, and this is your model equation. So wherever you see this Reynolds stress stresses, we are replacing this by this model form. Okay, so we will see what are the consequences of modeling like this. So we also discussed that the minus 2/3 k, the use of this minus 2/3 k, that is if the flow is completely homogeneous in all 3 directions, to save Reynolds stresses we have this minus 2/3 k, and I also discussed why 2/3 and all these things. And k is used because you want these Reynolds stresses are essentially turbulent stresses. So you want turbulent stresses to be modeled by a turbulent terms, not the flow term, right? So here you have essentially 3 quantities here, right? So this particular quantity here. So if you see this Sij bar, that is a mean strain gradient, so it's a flow term. So you are modeling turbulent stresses based on a flow term, which is not really great, but that's okay. But there are 2 other terms that you want at least to be turbulent, or you have a choice now. You can decide how mu t as well as k to be modeled, okay, because Sij bar is already a flow dependent parameter, it is not a turbulent parameter, right. So now there is also kind of misconception in some literature that eddy viscosity models, I have seen some students say eddy viscosity models or isotropic models. That is actually not true. It only promotes isotropy. So, eddy viscosity models by itself is not isotropic. Okay. So, it is simply called EVM or eddy viscosity models. By itself is not isotropic model, because you still have this strain rates Sij, which can help you to get anisotropic nature of the Reynolds stresses. But two terms, that is your nu t comma k, these two terms promotes or encourages isotropy, because these two are scalar quantities, but two terms are scalar and promotes isotropic behavior in the model. Okay, Sij will still help you. The reason I said that it is not isotropic, but it only promotes isotropic behavior. That is like, for example, if I take I equal to 1, j equal to 1. So, this is your minus u1 prime stress component. This is still now 2 nu t, right? You have Sij will give you half of that. So, it is basically you get 2 nu t dou u1 bar by dou x1, right? This is what you get. So, and then for I equal to 2, j equal to 2, the other component you get minus, of course you get minus 2/3 k. So, minus u2 prime, the exact one is replaced by the model, which is model is 2 nu t dou u2 bar by dou x2 minus 2/3 k. So, you see these two terms here, this term and this term, in a given flow, in a generic, I am just talking in a generic terminology, in a given flow these two terms need not be the same, right? Dou u1 bar by the gradient along the x direction or the gradient along the y direction of these two velocities need not be the same in general, right? And therefore, u1 prime bar and u2 prime bar are not isotropic. If these two terms are same, of course, then it is promoting isotropy. So, the strain rates will help you out in generic flows to get anisotropic behavior of the Reynolds stresses, but these two terms, this turbulence kinetic energy here, right? So, this k as well as the nu t, these two are scalar and they are promoting isotropic prediction inside the flow. So, they are working hard to get some isotropic behavior, which is not desirable, but the nature of the model is like this. Okay. So, this you have to remember. So, by default it is not isotropic, but there is some isotropic effect in the model when you use any eddy viscosity model. Okay. So, now still we have not found the final solution, because in the Rance equation we had 6 unknowns. 6 unknowns is replaced by now 2 unknowns, eddy viscosity and turbulence kinetic energy k. I still need access to this. So, we will start attacking one term at a time. We will take up the eddy viscosity, what it is. Okay. So, the eddy viscosity. Eddy viscosity. Now, already I told you that this has nothing to do with either any eddy, or you can say it is a some turbulent term. It has nothing to do with any eddy or viscosity. Okay. So it's better to call it some turbulence term, but anyway the name has become popular, so we call it eddy viscosity models or turbulence viscosity. And you see that now to get this we go purely on dimensional terms. So dimensionally this has to be meter square per second. Okay, for equation to be consistent, it is appearing next to the turbulence stresses are appearing together with viscous stresses. So nu and nu t can be written together, strain rate outside, and therefore meter square per second is the dimension for the eddy viscosity. So now that means I can come up with many arguments and options. For example, I can say now I want my eddy viscosity to be, for example, let us say depending on a velocity scale, a turbulent velocity scale and a turbulent length scale. Or I can say the eddy viscosity now purely on dimensional grounds depends on a length scale and a time scale. Okay. So where this u, l and t are turbulent velocity, length and time scales respectively. All right. So this is a turbulent scale at the end of the day. We want mu t to be depending on some turbulent scale, and as I mentioned, turbulent flows are characterized by many scales. There are many eddies, right? So which scale you want to consider here is a question, right? So note turbulent flows. Turbulence flows are multi-scale phenomena, right? There are many scales to be used, right? Eddies of many sizes. They all have their own turnover times or time scales associated with it. They are all moving at their own velocity and they are of different length. So now the question is which u, l and or t to consider for modeling. What do you think? What can we choose here? The nu t we need to model, and I am mentioning that it's a turbulent flows are multi-scale. Many eddies are there of different length, time and velocity, and therefore I mentioned eddy viscosity models are also statistical models. We go purely at statistical approach without considering any random component here. The moment we think of eddies, some random nature of the flow has to be considered for modeling, and this is a purely statistical approach. So therefore it's like a lumped approach. We are not really going to quantify and model any particular eddy here, right? So this question is very difficult to address in eddy viscosity models. Which particular eddy are we modeling here, right? We are trying to replace the entire Reynolds stresses in your flow here, the 6 particular terms, with this everywhere in the flow, and everywhere in the flow you will have many different eddies, and we are not trying to look at what is the energy associated with a bigger eddy and intermediate eddy and all these things. We are just lumping everything together and we are saying the 6 Reynolds stresses are simply depending on an eddy viscosity, a turbulence kinetic energy and so on, right? So that's why this model is very different. It's very basic approach, and obviously there will be errors associated with this, okay? Very statistical approach. So now we'll purely proceed based on dimensional arguments. So the answer of course is not favorable. It's a bit disappointing that no particular scale is being considered here, right? no particular or group of eddies are considered here. Right. So it's a purely statistical approach. The largest eddy is of course being resolved. You are not modeling it. That is the flow. Let's say in this particular room, what could be the largest eddy size? As big as this room, right? So that is you are going to capture. Your flow is going to capture that. But anything else you are not being capturing in this. Right? Everything else is being modeled except the largest eddy that is sitting. Every other eddy that is there associated with turbulence is being modeled in eddy viscosity models. So we will purely proceed. So the modeling will proceed on dimensional grounds. That is eddy viscosity has the same units as kinematic viscosity, meter square per second, right? So we need to find some velocity, length or time scale, and then we have different models for that. So we will proceed with looking into a zero equation model. So to get eddy viscosity, now we will proceed with, there are many options. The first and the easiest option is using what is called a zero equation model.